So now that we've talked a little bit about pH and how it relates to the hydrogen ion concentration, we're getting a little bit more specific with our equilibrium constant. So we know that the basic way of writing the equilibrium constant is writing KEQ. We've also learned you can write Kc, then it's written in terms of concentration. You can also write Kp, which is obviously in terms of pressure. Okay, when you talk about the equilibrium constant of a weak acid, you can use what's called Ka. And Ka, that A obviously stands for acid. Okay, and we know that it has an equilibrium constant because, again, the acid is weak, so the dissociation is not complete, and so you have an equilibrium system. Okay, and because since we have an equilibrium system, it's not possible to go directly to the pH by taking the negative log of the hydrogen ion concentration, because many times you don't know the hydrogen ion concentration without doing some type of math. Okay, so we know there's very little dissociation. The change in the acid concentration is going to be really small, so we still are going to be making ice tables for the weak acid, etc. So here it says make an ice table for the weak acid HA, and they do use HA quite a bit on the AP test. So just know that that stands for a weak acid with a starting concentration of 0.050 molar HA. So it would look something like this, our ice table. Okay, and so our initial concentration would be the 0.050. This is 0, this is 0. This is going to be minus X plus X plus X. And so overall, our ice table looks like this. Okay, and then write the Ka expression. The Ka expression would be the concentration of H plus or H3O plus times A minus. And one of the things you're going to notice quite often is those are pretty much always going to be X. And then 0.050 minus X, if we actually had to do the math, that's the part, remember, that we would take out. I guess I kind of combine those two different ways together. So that would be times the concentration of HA. So notice here that the way that they wrote that, because the hydrogen ion concentration and the conjugate base concentration are typically the same. Usually when it's a weak acid, you get one hydrogen that breaks off, and then you're left with a conjugate base, that negatively charged ion afterwards. And because you get a 1-to-1 ratio, basically you can say, well, whatever the hydrogen ion concentration is, that's what the concentration of A minus is going to be as well. So what that means, you could also write this like this, squared over the concentration of HA. Because that A minus and that H3O plus are the same, a lot of times you just, again, take that value and you square it. Now, another thing that you can do with the Ka, just like with pH, remember that pH is equal to the negative log of that hydrogen ion concentration. You have something that's called the pKa as well. Okay, and the pKa, don't think about anything more than this. It's just the negative log of the Ka. Why do we use pH? Because hydrogen ion concentrations are typically really small numbers, and pH gives us a more normal size value. Same with pKa as well. A lot of times these Kas are really, really small numbers, and so by taking the negative log of those numbers, we get a pKa, which is just a more normal looking number. Okay, so an example here, if ethanoic acid has a pKa of 4.74, what's its Ka? So if we know that the pKa is equal to the negative log of the Ka value, remember, how do you go the opposite of pH? You take 10 to the negative, not Ka, excuse me, 10 to the negative pKa is going to equal the Ka value. So we simply need to take 10 to the power of negative 4.74, and that gives us a hydrogen, or a Ka value, excuse me, of 1.82 times 10 to the minus fifth. Okay? And if you have a Ka value, so that's its Ka, so equals the Ka value. Okay? And if we have a Ka of 1.38 times 10 to the negative fifth, what's its pKa? Again, now we're just going to take the negative log of 1.38 times 10 to the minus fifth. And that equals 4.86. So you'll notice that the smaller, and this is the important part here, the smaller of the two pKa's, this is the pKa. So of those two acids, ethanoic and propanoic acid, ethanoic has the smaller pKa value, but it has the larger Ka value. And the larger the Ka value, remember the Ka value is nothing more than a comparison of the concentration of the products over the concentration of the reactants. The larger the Ka value, the stronger the acid is, the more that acid dissociates. So we can see here, based on this information, this Ka value and this Ka value, that this number is bigger than this number is. Okay, the 1.82 is a larger value. Therefore, that means that acid dissociates a little bit more. The ethanoic acid dissociates a little bit more than the propanoic acid does. So that means ethanoic is stronger. So which is the stronger acid, propanoic or ethanoic? Ethanoic. And why? Because it has a larger Ka value. So what generalization can you make about the value of Ka and the strength of the acid? The larger the Ka value, the stronger the acid. Okay, and then same thing, what about pKa? We know that the pKa is of ethanoic is lower than that of propanoic. So therefore, the smaller the pKa, and it's kind of like pH as well, right? The smaller the pH is, the more hydrogen ions there are, and therefore the stronger the acid is. So same thing here. Smaller the pKa, the stronger the acid. Okay? So example 4, now we're going to actually apply some of the stuff that we learned that we just used before. So what is the pH of a 1 molar solution of ethanoic acid? So the first thing we're going to need is we're going to need the Ka value, which is 1.82 times 10 to the minus fifth. So we're going to take 1.82 times 10 to the minus fifth. And again, remember this up here, that this equation here, I'm going to start doing these a little bit quicker just to kind of skip the ice table part of it. Basically what you're going to have, and this is going to look real similar, you're going to have x squared over 1 molar minus x, which again, we're going to leave that minus x out to, eliminate the need for the quadratic equation. Okay, so we're going to solve for that. And x, remember, is going to equal the hydrogen ion concentration. It's also going to equal the conjugate base ion concentration, the ethanoate part of that acid, the A minus part. Okay, so 1.82 times 10 to the minus fifth times 1 is obviously the same number. So now I'm just going to take the square root of 1.82 times 10 to the minus fifth, and that equals 4.27 times 10 to the minus third. And again, I could approximate the pH now because, again, my power is to the minus third. So I know the pH from what we've previously learned about pHs is that it falls between 2 and 3 somewhere. Because it's not a multiple choice question, I can actually figure it out. I'm going to take the negative log of that answer. And big surprise, 2.37 is the pH. Okay, example 5, just a couple more examples, and then we'll be done with these examples of Ka. So calculate the Ka value of a 1 molar solution of a weak acid with a hydrogen ion concentration of 1.75 times 10 to the minus third. So remember, if H plus has a concentration of 1.75 times 10 to the minus third, then so does the conjugate base, the A minus part as well. So therefore, we can say that the Ka value is going to equal 1.75 times 10 to the minus third squared, because that's H plus and the A minus component, whatever that conjugate base happens to be, over 0.100. Now remember, when it's an X, you leave it out. But when it's a real number, you leave it in there because we're not using the quadratic equation here anyway. We're just solving for Ka. So don't take that minus X part out because it's not an X. It's a 1.75 times 10 to the minus third. So I'm going to take 1.75 times 10 to the minus third. I'm going to square it. And now I'm going to divide by, and I'm going to put it in parentheses, 0.100 minus 1.75 times 10 to the minus third. And it might not make a huge difference in my answer, but that absolutely, you must do it like that. You can't leave that part out. You only leave it out like we did up here when you have that minus x. And you go, nope, that would require the quadratic equation. We're out. Okay? And so I get a final answer of 3.12 times 10 to the minus fifth. Okay, and then example 6 says calculate the Ka of a 0.250 molar weak acid solution with a pH of 5.11. So if I know the pH equals 5.11, then right away I know I can take 10 to the negative pH. So 10 to the power of negative 5.11, and that equals 7.76 times 10 to the minus 6. And again, what does that equal? That equals the hydrogen ion concentration. And it also equals the concentration of that conjugate base of the A minus from that in that solution. So that means the Ka is going to equal, now it looks just like example number 5. 7.76 times 10 to the minus 6th squared over the concentration of that weak acid. And again, in this case, that the X value, this value here is so small, it's not going to make a difference, but we still want to include it. Okay, so 0.250 minus 7.76 times 10 to the minus 6. So I'm going to square that number, 7.76 times 10 to the minus 6 squared. And then I'm going to divide by, in parentheses, 0.250 minus 7.76 times 10 to the minus 6th. And again, if you leave this part out here, you're probably going to get the exact same answer, I would imagine. 2.41 times 10 to the negative 10th would be this. So which of those two acids is stronger from example 5 and example 6? Well, this Ka value is only to the negative 5th. This one's to the negative 10th. What does that tell you? It tells you that this acid dissociates much, much more than the acid down here in example 6. This one with a Ka value to the negative 10th means you get very, very little product. So that makes it a really, really weak acid. Remember, the larger the Ka value, the more that acid dissociates and the stronger that acid is.